Waves in a stringed instrument. So in order to talk about waves in a string instrument, first we need to define the different types of strings. So there are mainly two different types of strings that we talk about. Ideal strings are perfectly uniform strings, uniformly dense, composed of uniformly circularly symmetrical material, produces a string that's perfectly flexible, amount of tension that is required to move a string a distance in any direction is absolutely perfect, and it offers no resistance to bending. It is ideal, and in ideal conditions, these are the strings that are going to be known. Real strings deviate from the ideal behavior due to the presence of some unintentional damping forces. The undesired damping forces introduce some level of inharmonicity into the system of vibration. This can be like an overtone that may be large or small, which depends on the strings themselves. For example, a thin string will have almost an approximate ideal behavior. However, thick strings will behave more like cylinders that have natural resonances that are not whole number multiples of the fundamental frequency. Reflection of a wave. So this is an animation that shows us a wave reflecting from an edge. So an incoming wave is a positive wave, strikes a wall boundary, and goes back as a negative wave, negative pulse. Okay, this is called a reflection of a wave. Now let's talk about how these waves are formed. So the first case, the one that we just saw, is from a fixed end, where a positive pulse coming in reflects back as a negative pulse. On the other hand, if you have a free end, which means that the other end is free to move, the positive incoming wave will return back as a positive outgoing wave. Some laws of reflection. So an incoming wave, for example, onto a reflecting surface, like for example, if we were to consider the example of air, the reflecting surface would probably be like a mirror. It will reflect back as an outgoing wave. These points on the wave are going to be called crests, and a normal drawn to the reflecting surface will indicate the incident angle and the reflected angle. So the angle that the incoming wave makes with the normal, which is 90 degrees to the reflecting surface, is called the angle of incidence. The other angle of outgoing wave is called the angle of reflection. Note very carefully that it is not the angle between the reflecting surface and the incoming wave. It is the angle drawn normal to the incoming and the outgoing wave. For a smooth surface, under ideal condition, the angle of incidence must equal the angle of reflection. There are two basic laws of reflection. One of them is, on an ideal case, on a smooth surface, the angle of incidence always equals the angle of reflection. Reflected rays lie in the same plane as the incident ray, and the normal to the surface at the point of incidence. The two rays are on the opposite sides of a normal. Normal is a line drawn 90 degrees to the reflecting media. There are different types of reflection. So for example, the first one is reflection from a plane barrier, in which there can be incident plane waves or incident spherical waves. The other one is reflection from a concave barrier. Let's talk about both of these cases. So a plane wave incident on a plane barrier will be reflected as shown in this animation. So a plane wave leaves the vibrating material, it reflects from it, and it is reflected back as shown in the animation. So a spherical wave incident on a plane barrier will be reflected back. Spherical waves usually are formed from point sources, and they can also be called spreading waves. Reflected waves will be spherical and will seem like as if they are originating from a source that is some distance on the other side of the barrier, also called the image source. So for example, this animation is very good to see the image source. So a wave source here forms a wave, the waves come forward, and then these waves are reflected back, almost as if the image is coming out from this area. So watch very carefully. So wave source forms, reflection happens. So almost like you're saying that the reflection is happening from a virtual image of the wave source. Plane waves incident on a conical barrier would be like this. Incident plane waves are coming in, as shown here, and then they are reflected back from the barrier as spherical waves. And plane waves are converted into a point source, so they will come back and focus on this point. The advantage of this is, especially when you can think of an antenna and it is designed to capture as many waves as possible, a spherical barrier would be a very good collector. So think of it as water coming down from a rain pipe, and in order to hold the water down, you need to put like a bucket underneath, which is almost going to be concave in order for it to hold water in. So when we talk about sound waves, the reflection of sound wave is also called an echo, as shown in this animation. If the reflection is off a nearby wall, it is called a reverberation. If it is from a faraway wall or a faraway distance, we call it an echo. Reflection in a room can actually hinder the sound production in different rooms. So in order for us to decrease the amount of reflection that is going on in the sound, we always put up sound dampeners around the room that always absorb the sound and don't let it reflect back. Theaters in ancient Greece around 500 BC were built utilizing this and more complex concept. They have curved spaces and they're cut into hillsides. Another really interesting application of reflection of sound waves happens in a whispering gallery. A whispering gallery is a specifically designed area that can carry whispers to other part of the room or the building. When you stand at particular points in a whispering gallery, which is called a focus point, and whisper, the whisper is carried distinctly to a listener at another point in the room. The building is usually constructed in a circular or an elliptical shape.